Beneath Utah's Great Salt Lake, the ground is stirring in unexpected ways. Deep quakes, strange movement, and satellite data hint at something massive rising below.
Hot, dry weather is bringing back serious concerns about the Great Salt Lake. Water levels are again dropping dangerously low, and those managing it say it's a problem that all of us need to fix.
Something vast lurks beneath the shimmering surface of Utah's Great Salt Lake. For decades, this inland sea has masked subtle but persistent secrets. Now, satellites are catching movement when nothing should move. Strange tremors are rattling the earth at impossible depths, in places once believed immovable. Shadows in the crust, hints of rising geological titans, have begun to flicker across scientific instruments, defying everything we thought we knew about the American West. Utah, home to high deserts and salt flats, is not a place where colossal underground forces are expected to awaken. Yet the ground beneath is stirring. Satellites paint an image of something vast and dynamic pushing up from the abyss. A 4.1 magnitude quake at 68 kilometers deep, a place beyond the reach of Utah's ordinary crust, has become a signal flare for geologists and seismologists across the globe. The rules of geology are being challenged, and the origins of this subterranean movement may have implications more far-reaching than anyone has dared to imagine. Is the bedrock of the West quietly fracturing under new, hidden forces? Or is something even stranger, deeper, and more transformative breaking through the crust? Let's descend beneath the Salt Lake, follow the clues etched by satellites and seismographs, and uncover the true nature of what's rising below Utah.
Chapter 1.
The Impossible Quake Mystery. The story begins not at the surface, but dozens of kilometers beneath it, where something extraordinary just happened. A magnitude 4.1 earthquake struck near Vernal, Utah. Unexpected, but not utterly unprecedented, except for one unsettling detail. This quake originated at a depth of 68 kilometers. By every geological principle, Utah's crust simply isn't that thick. Its brittle outer shell barely reaches those depths. So how can an earthquake occur in rock that shouldn't even exist in this context? Could there be a previously undetected feature or structure in the deep crust? Or is this a sign that our understanding of Utah's subsurface needs revision? Seismologists raced to analyze the event, and what they found cracked open a deep scientific mystery. Typically, earthquakes in the region strike within 10 or 20 kilometers of the surface, places where the crust is most likely to fracture. The brittle, rocky crust of Utah is relatively thin compared to the world's deeper tectonic basins. But nothing about this quake made sense. Its seismic signals suggested rupture far beneath the usual quake zone, in material assumed too hot and plastic to snap under stress. This single tremor, caught by sensitive arrays and satellites, is more than an anomaly. It's evidence of movement, vertical and horizontal, at the very base of Utah's lithosphere, a boundary never before breached by earthquakes in this area. If the deepest parts of the crust are trembling, what force could be responsible? Ancient wounds in the continental body, reawakened after eons. Others speculate about influences from below, powerful upwellings from the mantle, carrying heat and energy strong enough to deform the crust. Theories multiply, but every answer exposes new questions about the fabric of the land beneath our feet.
Chapter 2. Satellites spot the uplift.
The mystery doesn't stop with waves on a seismograph. Above, satellites circling hundreds of kilometers overhead are seeing Utah in a new light. Subtle ripples, measured in millimeters but spanning vast distances, are appearing where the land should be stable. Interferometric synthetic aperture radar, or InSAR, has mapped a slow, almost imperceptible rise beneath the Great Salt Lake itself. Why would the ground, long dormant, now flex upward? Could a previously obscured geologic structure be rising from the depths? Or is the mantle beneath Utah stirring to life? Satellite imagery eliminates much of the guesswork. Scientists superimpose recent ground movement atop decades of stillness and watch a pattern emerge. The ground is swelling. The deformation is not consistent with surface processes like groundwater extraction or sediment compaction. This is not the work of rain, drought, or human industry. Instead, the uplift points toward a force below, an engine of change at depths no mining drill has ever reached. Each new satellite pass captures the unmistakable fingerprint of a dynamic source. The question grows sharper. Is Utah's crust being inflated by intrusive magma, isostatic rebound as the lake dries, or could other, deeper phenomena be causing this movement? InSAR data suggest that the very shape of the lake bed is subtly changing. Teams mapping the region over the past 2 decades have found that the rate of uplift is not constant. There are pulses, periods when upwelling accelerates, followed by intervals of calm. These pulses appear to coincide with the timing of some minor, deep seismic events below the lake. It suggests a relationship. As something stirs below, the ground above swells in reply. The more scientists map, the more they suspect this is not a single phenomenon, but a series of related changes.
Chapter 3. Anatomy of Deep Earthquakes.
To solve the puzzle, scientists turn to places earthquakes aren't supposed to start: the deep, hot lower crust and the uppermost mantle. In most of the world, earthquakes happen where rock is cold, brittle, and liable to break. But at 68 kilometers beneath Utah, the environment should be more like slowly moving plastic than solid stone. So what could trigger a quake at such a depth? Is this a sign of mantle upwellings, or an example of deep faults being reactivated by changes in temperature, pressure, or composition? The vernal earthquake, deeper than the local crust itself should be, hints at rupture in regions long classified as immune to stress. Here, ordinary rules fail. Large earthquakes are extremely rare at such depths, but smaller tremors can sometimes arise from processes like fluid movement, phase transitions, or tectonic stretching in nearby regions. Scientists know that such depths are rarely the birthplace of earthquakes in continental interiors. Finding one here challenges the conventional model of the crust-mantle boundary and suggests a much more dynamic, perhaps unstable frontier beneath Utah. If earthquakes can start at the very roots of a continent, are there hidden weaknesses waiting for the next wave of energy? Such mechanisms lead some to speculate about deep focus, seismicity, although that is usually associated with subduction zones. Utah, however, is far from any modern subduction boundary. Some models propose that isolated, dense blocks of old crust or lithosphere may lurk deep below, concentrating stress until even hot plastic rock can rupture. As scientists debate these ideas, Utah becomes a window into tectonic mysteries usually hidden in the depths.
Chapter 4.
Clues in the concentrated hotspot. Craters, cones, and ancient lava flows shape parts of Utah's landscape, testimony to past volcanism. But the region around the Great Salt Lake has been quiet for millennia, its volcanic legacy mostly buried beneath salt and sediment. Now, with satellites observing and new seismic data emerging, fresh questions are appearing. Uplift and deep earthquakes are concentrated near dormant volcanic provinces. Is a mantle upwelling, similar to those found below larger volcanic hotspots, influencing this region? Areas like Hawaii, Iceland, and Yellowstone are fueled by deeper anomalies in the mantle. Utah is not traditionally considered a hotspot, yet the signs, uplift, deep minor tremors, and slightly elevated heat flow, prompt comparisons. Rock chemistry provides tantalizing but incomplete clues. Some ancient basalt samples from areas near the Salt Lake show certain features also found in known hotspot provinces, such as subtle changes in temperatures or gas ratios. Recent fieldwork has uncovered enduring gradients in heat flow, higher than in neighboring states and not fully explained by known sources. The question becomes stark. Could trace amounts of deep heat remain, or are we observing a different kind of mantle process, unique to the basin and range's complicated tectonic inheritance?
Chapter 5.
The tectonic boundary paradox. Utah sits far from the edge of the continent. Its faults, Wasatch, Sevier, and others, mark past tectonic jostling, but most dramatic Earth movements historically belong to the coasts and the world's major plate boundaries. Yet now, Utah's Earth is showing hints of movement as if pulled by unseen hands. Why here? And why now? Are larger tectonic plates exerting distant, unseen forces? Or is the continent itself flexing from inside out? Seismic waves travel the globe. Interior earthquakes, especially deep ones, are rare and enigmatic. With movement mapped by satellites in places long thought immune to major stress, Utah stands at the forefront of a paradox. Its quiet, interior location should shield it from dramatic change. But the Earth is stirring. Some theorists now see North America as a patchwork of microdomains, each with its own internal stresses. The Pacific Plate's relentless westward push stretches the interior. Stress can be transferred hundreds of kilometers away. GPS records show ongoing east-west extension across Utah, subtle and steady over the years. Is this a precursor to larger, more disruptive shifts across North America? And is our understanding of tectonic safety in the middle of continents due for a dramatic revision?
Chapter 6. Salt Lake's Deep History Unveiled.
Utah's Great Salt Lake is a relic, an echo of mighty Lake Bonneville, which once covered thousands of square miles. Over thousands of years, the basin has quietly accumulated salt, clay, and silt, hiding its deepest scars. But satellites and data from deep earthquakes are prompting a re-examination of that tranquil story. Is the ground beneath the lake truly as quiet as it seems? Or have the thick layers of salt and sediment simply muffled the activity below? Each tremor, each swell in the Earth's surface cracks open the lake's hidden history. Past flood events, slow tilting of the basin, and vanished rivers become new clues. Beneath the salt crust, faults may extend downward into territory still being mapped. Where the crust is thinnest, heat and energy may find an upward path. Core samples pulled from beneath the lakebed tell stories of long-buried landslides, sudden influxes of volcanic ash, and possibly ancient earthquakes. While large, historic quakes remain unproven, chemical traces in sediments hint at episodes of basin flooding that might be linked to distant tectonic activity or climate shifts. Even the physical layering of salt and clay, undisturbed for centuries, has begun to show minor warps and folds, like subtle ripples on a calm surface. Does the lake's own geology amplify or suppress the deep signals now being recorded? And could its sediments act as both cloak and conduit for larger, rising forces?
Chapter 7. Mantle Mysteries. Below Utah.
The mantle, Earth's convecting dynamic underlayer, sits tantalizingly out of reach, and in Utah, it may be making itself felt in new ways. Deep quakes and rising ground imply some dialogue between crust and mantle, a conversation being overheard by satellites and seismic arrays. What could motivate the mantle to impact the shallow crust here? Could past volcanic activity have left behind heat? Or is a broader basin and range extension allowing the lithosphere to stretch and thin? Some of the patterns observed resemble those found in regions of mantle-driven uplift elsewhere. Slow dome-like swelling punctuated by minor seismic noise. When deep rock warms and rises, it can weaken the crust, producing hints of movement not seen in long periods of previous calm. Seismic tomography, the imaging of Earth's interior using earthquake waves, has revealed slow zones beneath northern Utah, possibly indicating hotter or softer rock. Some researchers hypothesize the existence of an embryonic upwelling below, perhaps not powerful enough to create new volcanoes, but sufficient to destabilize the overlying crust. Does this mean new magma bodies are forming below? Or is this simply a fleeting pulse in the long history of the continent's interior?
Chapter 8. Patterns on the satellite maps.
With each satellite pass, a clearer picture emerges. Utah's underground story told through a flicker of movement here, a subtle bulge there. The uplift beneath the Great Salt Lake is not uniform. Instead, it branches and shifts, creating hotspots of deformation within a broader zone.
Why does the movement cluster in some places, but not others? And what do these patterns reveal about the structures below? Mapping the data shows zones of intense change, flanked by quieter stretches of ground. This map may trace the outlines of deeply buried faults, zones where fluids collect, or regions where the crust is especially thin. Closer analysis shows ovals of deformation, with the largest shifts near areas of lowest crustal thickness. InSAR data reveals faint pulses radiating outward, like ripples from a submerged source. In some areas, the ground even twists as it rises, revealing complex, multi-directional deformation. Computer models recreate these signals, proposing a tangled network of basement faults, long buried, now acting as channels for deep energy as it moves upward. Does this point to local weaknesses in the crust, a migrating pocket of buoyant material, or the dynamic interplay between old faults and new mantle activity? The data yields clues, but each answer leads to more questions.
Chapter 9. The paradox of Aseismic uplift. Movement, but silence. In many sectors under the lake, satellites show steady uplift, yet seismometers record nothing. The ground swells without quaking, baffling scientists and intensifying debate. Is this simply harmless settling, or could it presage future rupture? Aseismic, or quake-free deformation, can sometimes occur ahead of sudden shifts. Rocks flex, distort, and only sometimes snap. In geological conferences, experts debate, is this uplift comparable to the inflation of volcanoes before eruption? Or does it mark long-term warping, unlikely to end in disaster? Observations from elsewhere in the world show that years, even decades, of silent swell can occur before a major event. Fluid movement in cracks may permit stress to dissipate without earthquakes, but in other cases, this can be a precursor to more dramatic changes. Will Utah's next ground shift be silent, creeping, or catastrophic? Distinguishing normal crustal flexure from forerunners of disaster requires careful observation and patience.
Chapter 10. Ancient faults awaken?
Long ago, significant earth movements fractured Utah's surface, creating the valleys and mountains that define the state today. For centuries, most of these old faults have been quiet, buried beneath layers of younger sediment and salt. But the pattern of uplift and deep seismicity raises the question, could some ancient faults be responding to new forces? Are these old zones being reactivated, transmitting deep-seated energy towards the surface? Researchers return to old maps, correlating tremors to known fault lines and searching for minute signs of displacement. Modern tools like GPS and LiDAR can record shifts as small as a few millimeters. In the last decade, several such shifts have clustered along faults long considered inactive. Some geophysicists propose that fluids or temperature changes could be recharging these fractures, filling them with new potential. Could a chain reaction be underway, with movement at depth influencing faults that have lain undisturbed since Lake Bonneville's time? And if so, how might this subtle energy eventually reshape Utah's landscape?
Chapter 11. Microplates in the making. The great tectonic plates have not always been monoliths. They've broken, merged, and redefined Earth's surface countless times. Deep beneath Utah, is there evidence of incipient fragmentation? Is mounting pressure and deep, anomalous seismicity the earliest stage of local plate disruption? As the crust flexes and bends, tiny splinters may emerge, incipient boundaries for future microplates. Geologists search for telltale signs, zigzag patterns of quakes, subtle variations in ground velocity, lines where the Earth begins to move in different directions. Utah's crust may seem uniform from the surface, but deeper down, it is cross-cut by ancient scars, reminders of rifting and mountain building from long ago. Under renewed tension, these scars could become new fault zones, slowly dividing the region into smaller tectonic blocks. Will Utah's crust, considered a stable entity, morph into a patchwork of minor plates, each shifting in its own direction? The first signs are subtle, requiring more data and more time to confirm, but they hint at a changing geologic future. Chapter 12. The Great Salt Lake's Future Threat. As the ground swells and deep seismicity is tracked below, what does this mean for the people, towns, and cities that surround the Great Salt Lake today? The ring of mountains around Salt Lake City, the fertile valleys, and even the brackish salt beds owe their existence to ancient, powerful earth movements. Now, if new forces are awakening, how could that legacy change? Could the ongoing uplift and deep tremors bring new patterns of hazard, earthquakes in unanticipated places, gradual ground movement affecting roads and infrastructure? Even small movements, if persistent, can reshape the surface over years or decades. Urban planners, engineers, and policymakers are watching the data closely, updating risk models and emergency plans. The threat is not only from sudden quakes, but also from long-term changes, land rising or sinking, tilting the built environment, or altering the shape and extent of the lake. These shifts, though slow, can have real impacts on communities. The evidence so far is suggestive, not definitive. Scientists remain cautious, recognizing that the full story is still unfolding beneath Utah's largest lake. Chapter 13. Lessons from the Ring of Fire. Across the Pacific Rim, colossal earthquakes and eruptions have long shaped coastal civilizations, reminders that invisible stresses can erupt into unstoppable change. The Ring of Fire's history is packed with warnings about how energy stored within the earth can find release, sometimes with little forewarning. Are Utah's recent deep tremors hinting at similar processes, even far from the nearest oceanic trench? In the world's most active tectonic belts, minor deep earthquakes and subtle pulsing of the ground have sometimes preceded larger events. Comparisons can instruct. In the Ring of Fire, geologists learn to watch for small, enigmatic signs, earthquakes at depth, far from the main danger zones, ground heaving long before visible cracks appear. In the valleys and deserts around Great Salt Lake, ancient features, dried riverbeds, tilted land, and sediment layers bear witness to past upheaval. While Utah's risks are distinct, the lessons of global tectonics urge careful observation and humility before nature's power. Chapter 14. The clock ticks below. Beneath the dry lake beds, a slow competition unfolds between ancient and modern forces. Historic faults relax and accumulate stress, while deep movements in the mantle may alter the architecture above. Can scientists anticipate the next major event? Are there patterns in the satellite and seismic data, or is Utah's future written in ambiguity? Each tremor and each centimeter of uplift ticks the geological clock forward. No one knows when the next big shift will arrive. To improve forecasts, a network of sensors, GPS stations, and remote sensing instruments now focuses on the Great Salt Lake. Computer models sift through billions of data points, searching for patterns that could signal change. Yet the Earth keeps its secrets well. History tells us that dramatic changes must come, but not precisely when. Utah, too, must wait and see, its fate in the slow hands of the planet's deeper rhythms. Will the transformation come in a sudden event, or gradually over centuries? The region's silence is punctuated by subtle signs that suggest the story is not yet complete. Chapter 15. When Giants Awaken. The restless stirring beneath the Great Salt Lake may be only the beginning, a first subtle movement as tectonic giants shift in their ancient sleep. Each quake at improbable depth, each ripple mapped by satellite, is a chapter in an ongoing story. Utah, once considered a land of tectonic quiet, could be on the threshold of a new phase, one that echoes tectonic transformations elsewhere on Earth. Deep beneath the salt, forces are moving. Processes that have shaped whole continents continue, hidden for now, but building toward an uncertain future. No place on Earth is truly immune, not the Pacific, not the Wasatch, not even the silent lakes of the interior West. What will change when Utah's deeper forces finally surface? As scientists and citizens maintain a vigilant watch, One thing is clear. The ground beneath the Great Salt Lake is alive, dynamic, and enigmatic as never before. In the years and decades ahead, Utah may indeed become the heart of a new geologic chapter, a place where ancient stories and new discoveries meet, and the future pulses deep below.